Okay, here we go. Second semester chemistry in 181 slides. Chapter 14 and 15, all about acids and bases. Great part about this chapter is it's a lot of review. Remember this table. How do we name acids? Make sure we know those. So work yourself up. Is it binary or oxy acid? And then go on through, okay? Make sure, remember binary, it's got the hydro, oxy, no prefix, ate to ick, because when you ate something bad, you say ick, and then ite to aus, because, that just sounds right. And make sure you know how to name them fully. This slide helped out some people that was kind of confusing on your support sheet. So on your support sheet, you had the example with chlorine here, but there was an asterisk letting you know that it could be also be for bromine and iodine. And these were the ones where it's like, if it was, if it was BRO, right, that'd be hypobromite, right? But if it was IO2, that's going to be iodite, or HBr, HIO2, HClO3, that's going to be chlorate. So I don't want to say interchangeable, but chlorine, bromine, iodine all go by the same rules depending on the amount that's in each of these compounds. Base naming, probably the least difficult thing we do, is the cation, and then you slap hydroxide at the end, essentially. NH3 is going to be our exception to that. NH3 is a base, but for the rest of them, cation, like sodium, hydroxide. Potassium, hydroxide. Magnesium, hydroxide. It's good to know the properties. We did some work on the properties versus acids and bases, so make sure you know this table, the differences and the similarities. Remember, acid-base reactions, when we do a neutralization reaction, you get a salt, one of the salts, and then water. Just do the double displacement, and you can see the salt that results, and then the water. And I think this is actually a typo. This isn't pH paper, this is litmus paper. So pH paper is going to change a different color based on the pH. This is litmus paper. So litmus paper, base turns it blue, B and B, acids turn it red or pinkish. For acids and bases, we talked about 3 different types of reaction: the ionization, dissociation, and neutralization. So remember, acids actually ionize. H2O is part of the reaction because it ionizes. This dates back to that whole net ionic equation. H2O is changing, so it's not a standby, right? So the hydrochloric acid, actually, the water will ionize, pull that hydrogen off, and then create the hydronium ion here, H3O+, and then the chloride ion, Cl- there. Dissociation is going to be a little bit different. Dissociation, the water doesn't pick up anything. Water doesn't change, but what water still does is it breaks them apart. Now, if you remember, polarity and strong pulls, so water is going to sort of split this cation, anion, and turn them into their ion form in solution. Aqueous in solution. Last one is the neutralization reaction we talked about, and that is an acid and a base together. And remember, this is a nice double displacement reaction where the cations can kind of exchange, kick each other out, and then you get your salt, NaCl, for this case because it's sodium, and then H2O, which is our water. So remember, you always get a salt and a water. Don't forget the world of titrations. Make sure you can, 1, explain to us how to do a titration, and 2, show how to do the math of it. When we're doing our calculations, you can break it up into the 3 steps. So when you're doing a titration calculation, you have a known molarity, and you know the volume of that you use. So you use that known molarity and your volume to calculate the amount of moles used. Then you go ahead and come to step 2, write out the neutralization reaction, and you do stoichiometry to do the mole-to-mole ratio, which will get you to the unknown. And then you use what you have in number 2 to come down through here. And so now you have the moles of the unknown, because you have the moles, and then usually you have the volume, or if you're going backwards, then you'll have the moles and the molarity. You got to find the volume. But a lot of times in titration, classic titration reactions, you know the volume used, and then you discover the moles, and you can use volume and moles to calculate the molarity of your unknown. Don't forget the pH scale and what that tells us. Remember, for our purposes, we're going from 1 to 14. 7's in the middle. It's the neutral pH. As you get closer to 1, it gets more acidic. As you get closer to 14, it gets more basic. The way we calculate our pH is we use either the hydronium concentration or the hydroxide concentration. Think back to the ionization and dissociation reactions. Those are where we create hydronium or hydroxides. Okay, in water or water for my people from Jersey. Okay, 25 degrees Celsius water. That's where we're going to be a very, very neutral liquid. But the hydronium is going to be 1 times 10 to the negative 7 concentration, molarity, where hydroxide will equal it out, and that will actually give you your Kw that we can use in our pH calculation. Here's our Kw here. Okay, remember it's the ionization constant, so the Kw is going to equal the product of the hydronium and the hydroxide concentration. So you multiply them together, that'll give you your Kw, and that will help you out because if you know 1, you can use Kw. Kw is always going to be 1 times 10 to the negative 14. So if you know Kw and you know the hydroxide concentration here, you can calculate the hydronium concentration. Here's a reminder how to do that. Okay, so if you have a balanced reaction, you go ahead and figure out the molarity of whatever you produce, and then you use your Kw to calculate the molarity of other. Okay, an example here. So if I give you 0.1 molar HClO4, I can then calculate the hydronium concentration from that, because I know this is going to be ionized and give me hydronium. Okay, so I do my mole ratio to calculate hydronium concentration, and then I go from there to here using the Kw. And that's going to help me figure out both hydronium and hydroxide concentration. The nice part about this is I know that this is going to be an acid, and so my hydronium concentration should be greater than my hydroxide concentration. And then we can use our hydronium and hydroxide concentrations to determine our pH and further determine if the solution is acidic or basic. Remember to use what you know and use the correct equation here. So if you know the pH, or excuse me, if you know the hydronium concentration, then use this one to find the pH. If you know the hydroxide concentration, use this one to find the pOH. And then depending on what you know there, you know pH plus pOH is going to equal 14. So you can do some simple math there. We want to find pH. We work in the pH scale. So if you've got a basic solution, you know the hydroxide concentration here, find pOH and then plug into here to find your pH. 2 equations I didn't make a slide for because we worked through the math of this in class, but if you know the pH and you're asked to find the hydronium concentration, and then this 10 to the negative is really the anti-log. So if I know the pH, I can do 10 to the negative pH, and that will give me the hydronium concentration. Same thing down here. If I know the pOH, I can use that to find the hydroxide concentration. So same equation, just rewritten. That's your basics for your acids and bases. Remember naming, remember titrations, remember pH and pOH, and remember how to do all the steps and the calculations.